So, I think we're just going to keep going. So we are doing page 440, number 73. If somebody would read that for us, please. Somebody has to have a book. Yep. Okay. So let's start here. So here's my spring. Here's my mass on a spring. And I know that this is stretched 9.6 centimeters. Okay. So this is part A. So why is the spring stretching? Yeah, because gravity's pulling on it. Why is the mass not falling all the way to the ground? No. Right now in part A, it's just hanging there. There's no simple harmonic motion yet. Not to a string, but a spring. Okay, so what's the force? It's that's where we're going, okay? So here's my block, and you told me that there's a gravitational force going down. And there's also going to be, you keep saying that the block is attached to the spring. Now, I was waiting for somebody to tell me it was a tension force, but it's not a tension force. It is an equilibrium, which is what Maddie said, okay? So it's not a tension force because the spring stretches. All right. And if you remember, for chapters and chapters and chapters, every time there was a string, it was a non-stretching string. Okay, specifically for this reason. The string. I know, but I'm saying that's why it's not a tension, is because a tension is a single force. And for many chapters, when we had a string, it was always the same tension, but it always said that it was a non-stretching string. And now that we're talking about a spring, we have to use the spring force instead of a tension force. So, oh, it's just there. I mean, I should probably draw my picture this way. Here's the spring with nothing on it at its relaxed length. Here's the spring with the mass on it. And then this distance is the 9.6 centimeters. Okay. So we'll let up be positive y, just because. So we can say that F net y is equal to 0. This is an object in equilibrium, and not only equilibrium, but static equilibrium. It's just sitting there. So we're going to skip a few steps here and say that the magnitude of the spring force is going to be equal to the magnitude of the gravitational force. So I've got Kx is equal to mg, or K is going to be mg over x. So I think m was 1.3 kilograms, and x is 0.096 meters. So what do we get for our spring constant? So Casey gets 133. 133 what? What's the units? Units. Yeah, but that's kind of wacky. So what are kilogram meters per second squared? Newtons. So actually the unit that we usually use is a Newton meter, which if you think about F spring is equal to Kx, makes sense because the spring force would be in newtons. If K is in newtons per meter and X is in meters, then those cancel and you end up with newtons. Okay. And we're only supposed to have 2 sig figs, so K is really equal to what? 130. All right. So, part B. What are we supposed to find in part B? No. What does part B ask us to find? Oh, it does. Oh, it was the period. Okay. Okay. So how do I find the period for a mass on a spring? Yeah, but we had a specific formula for this. 2 pi m over k. You can always look at the units and see if you're right. So remember that it doesn't depend on the amplitude. So it doesn't matter how far I pull that mass down. So I've got 2 pi, 1.3 kilograms divided by 130 newtons per meter, which, as you recall, you said a few minutes ago was really kilograms per second squared, which makes a little more sense now, but we're still not going to use it. Doesn't matter. I get 0.63 myself. And what are the units? No, the kilograms are going to cancel. And you end up with 1 over second squared. Right? Because this is going to give you kilograms. Newtons are going to be kilogram meters per second squared. So your kilograms, per meter. Your meters, so you have 1 over second squared, which is second squared, and then we square root the whole thing. Okay. All right, how about part C? Yep, now you can do 1 over period because you had it. Saying that period was 1 over frequency wasn't really helpful because we didn't have frequency yet. So what do we got? Okay, and what are my units for frequency? Yeah, second to the negative 1, but we call that a hertz. And here's part D that I really thought was part B, which is to find the amplitude. What's the amplitude going to be? What is amplitude? The max value of what? From the what? It's the max value of x, not just from the center, but from the, you could say the point of rest, the point of equilibrium. So what's the distance that this is moving from equilibrium? How far did you pull the, what? No. Was point what? This gives you your new equilibrium position. Okay? And then what do they do in the problem? By what? They stretch it by 5 centimeters. So it's that 5 centimeters that you pulled it down from equilibrium that is the amplitude. Okay? And then what's the last thing we're supposed to find in part E? Okay. So the max speed or the velocity amplitude, what's that symbol that we used for that? No, it's not omega. Yeah, it's Vm. And what's Vm equal to? Yeah, I know what the words are. I'm looking for an equation now. Okay, so go back in your notes. What's Vm going to be? Like that? It doesn't matter. I don't care about the negative sign because we're just finding a magnitude here. No, it's not the cosine of that jazz because that would be v of t. And actually, isn't it sine? With the negative sign out front? All I want is what that is. Because what the cosine function or what the sine function tells me is that this is my maximum velocity. And I'm going to be somewhere between my positive maximum velocity and my negative maximum velocity because my sine function is going to go between 1 and -1. But I just want to know what that maximum value is. Okay? So this is pretty good. I know what xm is. What's omega going to be? Yes, omega is the angular frequency, but I need to figure it out, so I need a formula. What is it? Okay, 2 pi over the period. So what do we get? Okay. All right. So we've looked at masses on a spring as simple harmonic oscillators. And now we want to look at some other things. So we're going to look at a couple different kinds of pendula. And the first type of pendulum we're going to look at is a torsion pendulum. And a torsion pendulum, nope, we'll use torque in a minute to do something else, is a disc with an axis through the middle, an axle through the middle, and it twists back and forth. So there's got to be some kind of spring mechanism involved. And basically, some mark on the pendulum oscillates back and forth between two angles, negative theta m and theta m. So the thing just twitches back and forth, rotates back and forth. And instead of having a spring constant, there's what's called a torsion constant. And that torsion constant, as you read, isn't a K, it's a kappa. And you make a kappa a little different. I mean, that's kind of what it is. If you look in your book, that's a lot what it looks like. So the period associated with this is going to be 2 pi times the rotational inertia over kappa. And we use rotational inertia here because you know that when you have things that rotate, it matters not just how much mass there is, but how that mass is distributed. If you had a hole in that disk, it's going to do something very different than if it's a solid disk. Okay? So that's kind of all we're going to talk about there. The more complicated thing, or the thing we're going to look at in more detail, is the simple pendulum. And so a simple pendulum is a mass on the end of a string of length L. The mass is called a bob. I don't know why, but it is. And there's a pivot point up here. And ultimately, what we want to find is an expression for the period of the pendulum. Just like we had one for the mass on the spring, we took one for the torsion pendulum that was based on the mass on a spring. And we want to find the period of this simple harmonic motion that we're going to have with a simple pendulum that swings back and forth. Okay, everybody got what they need? All right, so we're going to start by looking at the restoring force, actually. So here's going to be my pendulum. We assume that the string is massless, unstretchable, all those good things so that we can ignore it. And what are the forces that are acting on my pendulum bob? There's a gravitational force. And what else? No, let's not talk about the restoring force yet. What else is acting on the pendulum? There's a tension force. Okay. And And if the pendulum is swinging this way, which way does the restoring force have to point? Where does the restoring force always point? Think about a mass on a spring. Towards the equilibrium position. Where's an equilibrium position going to be for a swinging pendulum? When it's straight up and down, right? Okay, so that means that the restoring force, whatever it is going to move this way, tangent to that path. So what's going to be supplying that restoring force? Yeah, it's going to be a component of gravity, okay? The tension is, of course, radial, so it's perpendicular to the direction that we're talking about. And restoring force is often kind of like centripetal force. It's not a force that we put in a free body diagram. It's the result of other things. So when we have a mass on the spring, the restoring force is the spring force. And when we have a swinging pendulum, the restoring force is what I'm going to call the tangential component, so FGT, of the gravitational force. Okay? And if I'm going to assume that I'm pulling my pendulum out by an angle theta, then this angle is theta. And the magnitude of FGT is going to be mg sine theta. Okay. Tangential. All right. Yes. All right. So now, for my next piece, back to finding the period. For all simple harmonic oscillators, the period's equal to what? What else is the period equal to? 1 over f, which is cool if we have that, but we don't. So what else is it equal to? 2 pi over omega. So I've got something that's kind of moving in a circle. So we'll see if that takes us somewhere. But basically, if I can find omega, then I can get the period. Okay. So remember, if this is simple harmonic motion, then x of t is equal to xm cosine omega t plus v. V of t is negative xm omega sine omega t plus v. And A of t is negative xm omega squared cosine omega t plus v, right? We went through all those first or second day. Probably not. It's something that might come back later on if you take a higher level mechanics class or you take some specific kind of engineering class that would involve that. Okay. And remember even further then that A of t is negative omega squared x of t, right? Because this part and this part are that. I'm talking about stuff that's moving through angles. So I probably want to write this as alpha of t is negative omega squared theta of t. So maybe if I find alpha, I can find omega. And if I have omega, I can find capital T. Okay. So what kind of equations does alpha come into? It's in the equation for torque. Okay, and what's net torque equal to? I alpha. All right, so let's look at that for a minute. So we've got that restoring force, right? And so what would the torque of the restoring force be around the pivot point? So hang on, let's just remember in case we've forgotten, okay, that torque is what? RF sine phi? Okay. So what's my R going to be? L. What's my force going to be? Okay. Go ahead, Casey. No, because remember it's the angle between R and F. So if I go back to here, this is effectively my R. Here's my FG. Here's my restoring force. So the angle between them is actually 90. Okay. Oops. So this is actually times the sine of 90. Okay. And because the restoring force acts to make the torque smaller, there's a negative sign. Or actually, we could really just say that it's acting in the clockwise direction. Actually, I like that answer better. So it's a negative torque. Okay. All right. So my torque is going to be negative LmG sine theta. And then I also know, as we just said, that torque is equal to I alpha. Now, what's I going to be from my pendulum bob here? ML squared. Okay. Well, I want to write one thing for a minute here. Okay, so we could say, if we stick with the I alpha for a minute, okay, we could say that alpha was equal to negative LmG over I times sine theta, which we're going to come back to in a couple minutes, which is why it's important. And then actually, we need to make an approximation here in order for this to work. And it's called the small angle approximation. And it's actually a function of linearization. So if my function f of x is equal to sine x, and I set my approximation around 0, then you may or may not recall, but the linearization is f of a plus f prime of a times x, right? Calc review, a million years ago, about right? Okay. So what's f prime of x? Right. So I can say that L of x is equal to f of a, and what's the sine of 0? 0. Plus f prime of a, and what's the cosine of 0? Times x. So what this tells me is that for small angles, and even though you have to do this whole thing in radians, theta's got to be less than about 15 degrees. I can say that the sine of theta behaves like this. And we'll do like one or two. So here's theta in degrees, here's theta in radians, and here's sine theta, because you got to be in radian mode or it doesn't work. Okay, so 1 degree, so that's going to be 1 degree is 180 times pi, right? So it's pi divided by 180. No, 3.14 divided by 180 is not equal to 1. So make sure you're in radian mode and take the sine of 0.017. It's what? Take 5 degrees. What's 5 times pi over 180? And take the sine of 0.087. 10 degrees. That should be 0.17 radians. So what's the sine of that? Okay. 15 degrees. That should be 0.257. Oh, yeah. Oh, actually, I don't get 260s, but whatever. So what is it? Okay. So it's not working as well. And we've talked about this. When you get away from where the approximation is centered, it's not really working. So we're just going to try one more. We're going to try 30 degrees. Okay. And that would be like what? 0.544? No. I don't know what that is. I give up. I'm too hungry to do math in my head. What is it? 524? So as we get farther and farther away, it doesn't work as well. We'll finish this up